admittance form of primitive element we have seen, and finally we could conclude as a vector of I plus vector of j is equal to vector of v and a matrix y primitive was discussed. Now we stopped exactly at the corner. We wanted to understand what are these things. So these are the injection of current. So I would like to say it's called primitive. Let me highlight it. Primitive element, primitive matrix of element, which is in admittance notation. Why is there? It should be admittance only. This is vector of branch voltages, like a kth branch, which you have taken example between P and Q. Let the current injected be IK, voltage across the branch PQ be VK, and voltage source in the path which was independent voltage source VSK, and the current across the path was JSK, and the impedance or admittance in the path was mentioned for our analysis. So in that regard, this stood as a vector of branch voltages like VK, V1, V2, V3, Vn, etc. So this is called equivalent current. Equivalent current in kth branch. I should say across. I wrote it as an across. Let me write it clearly. Across the branch, because I am not writing kth branch here. Across the branch. This is current through the branch which you are considering. Like if k you are considering, it become Ik. If you are considering 1, it become I1. If it is fifth, I5, etc. It means to say this was the landing point we got. Set of current which are actually flowing in all the branches of the network. Equivalent current got transformed JSK and product with VSK and Y admittance of the branch into a current source which is called equivalent current source in that particular observation. So a current source across the branch and voltage like V1, V2, V3, the branch which you are considering, that voltages were put as vector of voltage and product with Y1, Y2, Y3, YK, etc. as applicable. I would say this matrix represents set of elements which are there in the network. Imagine n bus system. Imagine there are 1000 elements. The elements which I am speaking connected between bus 1 and 2. If I label it as element number 1, say Y1. The element between bus 2 and 3, if I call it as element number 2, like Y2, Y3, Y4, Y5, Y6, all together in the system. How many elements are physically present? Those are all the elements. I should give nomenclature like Y1, Y2, Y3, Y4, etc. in terms of admittance notation. If it is so with the impedance notation, I should refer it as Z1, Z2, Z3, Zn, etc. No matter, we are discussing admittance form of the representation. Hence, I stick on to elemental representation in terms of admittances only, like Y1, Y2, Y3, Y4, etc. All those elements, Y1, Y2, Y3, Y4 are confined into a matrix. That matrix is known as primitive admittance matrix of the system. Therefore, what are the characteristics of this? If I expand this matrix, what I should get? I1, J1, V1, Y1. If I use when I say vector, it must be a vector of I1, I2, I3, I4 in the column manner. When I say J is a vector, it will be J1, J2, J3, J4, J5, J6, a column of currents, equivalent currents from that transformation. And when I say V, a vector of branch voltages, it should stand as matrix V1, V2, V3, V4, V5 in a matrix form. And similarly, when a product need to be taken with respective voltage and respective branch element, this must be a matrix. You cannot multiply simply. When you have two matrices to be multiplied, you have a rule. Therefore, this primitive elemental representation of the network shall be put in the form of rows by column, which we call as a matrix. No doubt, this is a matrix by column, hence a column vector. Column vector, column vector. This is having a rows and columns, hence this is a matrix. Then where all the elements are placed? The elements are placed on the main diagonal of the matrix. Let us draw one rough view of Y primitive notation. Let us identify what are those elements, where all elements fall, when do they fall in that location. If we understand, it is very necessary for us to take up next step called as formation of Y bus of a system using singular transformation method. Okay, let us take, after having stopped at this point in the previous discussion, I began from this point where we exactly stopped. I would like to project what is this, and I recall back, this is a generalized equation. This I contains set of I1, I2, I3, J contains set of J1, J2, J3, J4, etc. and V contains V1, V2, V3, branch voltages, etc. And this matrix accompanies number of elements along its diagonal and off diagonal if there is a mutual coupling, which we will not speak right now. Let us write it and let us understand that. Okay, so I'll just take this. Okay. Primitive admittance matrix, I'm writing it as. This is called YPRI. Let me write it in the form of. So I may have the element noticed in this way: Y1, 0, 0, 0. I just take 0. Nth order I just take. Then I make 0, Y2, 0, 0, and 0. And similarly, I go with 0, 0, 0, 0, YN. If you want, I may write YK. Let me write 0, 0, 0. Somewhere I make dot here, I make dot. But there is a break here. Number of rows are present. Number of rows are present. In between, I am presenting one of the row, which represents, say, YK 0, 0. Okay. So what do you mean by this by observation? Y primitive element is having elements in this representation. The diagonal contains admittances of elements of the system, like Y1, Y2, Yn. Off diagonal are basically 0 when there is no mutual coupling. It means Y1 refers, if I really want, I can make still a correction like 1, 2, K, N of the element. Similarly, I can make 1, 2, somewhere here K, here N. It's N cross N representation. Okay. So it's a N cross N representation which I am trying to put over here. I confine it here. Okay. Then the characteristics of Y primitive matrix are the principal diagonal contains the elemental admittances. If I project you a simple example, if you wish to know where all this is represented, suppose if I draw a representation like this, let us hope this simple example for your understanding. Let's say this is a 4-bus system I would like to represent. Suppose this is bus number 1, bus number 2, bus number 3. No matter how I write it, how I account do really matter. Okay, I have 4-bus system. I would like to represent the element. Suppose if I call this as element number 1 with the elemental data Y1. I may even write this as 1. 1 refers element number 1 whose admittance I must be knowing. Otherwise, this is Y1 for me. If I say this is element number 2, this is element number 3, this is element number 4, let's say. What exactly it represents for you? It represents 4 elements of this system. How Y primitive matrix of this system can be framed using this concept? It should be Y primitive equal to, first is dimension of this. What is the dimension of this matrix? The dimension of this matrix falls number of elements. How many are there in this? Suppose if I find a n bus system, I may write here n cross n. Now in this problem, I have 4 here. Then dimension shall be max of 4. 1, 2, 3, 4. And again I write 1, 2, 3, 4. Okay. Now where all these values will find? Suppose this one is having say 0.2 more. Let us say this is having 0.15 more. Let me write here more. And this is having 0.10 more. Let it have 0.25 more. For example, no matter what the values are, what matters to me is how to place them and where to place them. Okay? I hope you are getting this. Then when I want to write this in this matrix, look at this. 1 cross 1. What is the value? The elemental admittance. Can you see here? 1 means element number 1 admittance at 1 cross 1. Same as element number 1. You may ask me how you wrote these numbers. If I have been given elements mentioned already in the system, I should use the element number. If I have not been given element number, I am free to allocate the numbers. Let us allocate and utilize them systematically in the manner which you have configured. Hope so. It was not given to me. I only have configured 1, 2, 3, 4 like this way, whose data is given to me in the form of a table. I could represent them. Then my next duty is to take this 1 means value of this one in this position. It is 0.2. Then where is the element number 2? Element number 2 is here, 0.15. This 2 cross 2. This is 0.15. Where is element number 3? Between bus 3 and 4. It's 0.3 cross 3. This is 0.10. Where is the last element? 0.25. This is element number 4. 4 cross 4. 0.25. Hope you are following me? 0.25. Very simple. Now I placed all these elemental representations, admittances along the main diagonal, which I mentioned here. The main diagonals contain the elemental admittance of the system you are considering. What about the off diagonals? off diagonals are basically 0 unless and until there exists a coupling between any of the lines with them, it stands 0. Let us take the first statement. Off diagonals are basically 0 means what? I will be placing 0, 0, 0. And here 0, 0, 0. And again here 0, 0. Place a 0, 0 here. Now you could find I formed Y primitive matrix of this example using the basic observation. The characteristics of Y primitive matrix shall be like this way. Principal diagonal contain elemental admittances represented 1 cross 1, element number 1, 2 cross 2, element number 2, so called n cross n at the last. This is the first principle. Suppose there exists a mutual coupling. What do you mean by mutual coupling? This is the point. Off diagonals are basically 0 when there is no mutual coupling. If there exists a coupling, if coupling exists, what do you mean by this? If coupling exists means element number 1 is mutually coupled. So there is a coupling between this and this, magnetic coupling between them. Then I would say mutual admittance, like impedance form, mutual inductance, what we call it. When two coils are kept neighbor, there exists a property self-inductance to both of them, as well as mutual inductance between them exists. So that phenomena I am trying to locate here. When these two transmission elements are possessing self-admittance, in the sense self-reactance, when I convert it to admittance, it becomes self-admittance like Y1, like Y2. If they do not have mutual coupling, then off diagonals of this row, element number 1 I am speaking, element number 1 row remains blank, 0, 0, 0, except 1 cross 1. Suppose there is a mutual coupling between 1 and 2. If coupling exists between element 1 and 2. It's an example, case study. There exists a mutual coupling between element number 1 and 2 by Y12 by value 0.01 more. Let's example. It should be negative. I'm just writing. By chance, there exists a mutual admittance between element number 1 and 2. Where do I represent this value? This value refers Y12 same as Y21 because it's a bidirectional. So Y12 refers elemental mutual admittance between element 1 and 2. Same as with respect to 2 and 1 by the value example 0.01 more. This I am going to represent over here 1 cross 2. This will be now 0.1.01. Hope you got this now. Similarly, when it is 1 2, how about Y21 is equal to Y12? Then I'll be touching 2 cross 1 is also without fail. Now you watch my matrix. Originally, when this if coupling exists case was not discussed, when there is no mutual coupling, triangle, lower triangle representations were perfectly 0, which I did in the original case. When I took a study, there can be a mutual coupling between any of the transmission lines in the system if there exists a mutual coupling. So like this, mutual coupling between element number 1 with the 2 with a mutual admittance. Let's say mutual admittance be 0.01 more. Then I should represent Y12 and Y21 with the representation value given. You can see this matrix got now modified to represent the exact relationship between element number 1 and 2 if there exists a coupling. So I have taken a case, let there be a coupling between 1 and 2, then 1 cross 2. 1 cross 2.
Sir.
I am going to tamper by 0.01 value more. Similarly, y21 I am going to tamper. Now this got represented as elemental mutual coupling is put in this matrix. This is called the actual representation of. You cannot say there exists a mutual coupling between any one line. There can be number of transmission lines having mutual coupling between number of other transmission lines. Then those many mutual couplings, if you get, those many non-zeros will be found here. It means basically zero if there is no coupling. If there exists a coupling, that coupling will represent its truthful mutual admittance in the position mentioned. Suppose if I call this line is also having coupling between 1 and 4. Let's say this is y12, y14. You may have transmission line, one is mutually coupled with 2 with the y12, as well one is mutually coupled with 4, y14. It may have a coupling with 3 also, no matter. In reality, how is that line going in the physical transmission layout? Really very close to each other? Are they really finding a mutual coupling among them, or they are isolated perfectly from each other? That matters. Whether there is a coupling or not, respective representation should be accompanied in the matrix, because this matrix serves as a backbone for us to represent elemental interconnection into system admittance bus. So this is called primitive work one need to take into. Suppose if it is y14, let us say y14 is equal to y41 by say 0.1 more. Let's say an example. Then how do I represent it? It's represented as 1,4, row number 1, column number 4. I am going to modify. This will be modified as 0.1.
Excuse me, sir.
And look at it. Hello, please.
Hello, sir.
Am I audible to you?
Board is looking blur, sir.
It's almost camera is very close. How come it is working? I will try. Okay. I will try to zoom it. Let's tell me whether this is coming clear to you or coming blur to you.
It is blur, sir.
It is blur, na? Okay. I'll go opposite. No, again blur.
Yes, sir.
I think I am trying to maximize it. I am very close to the point of final value, I think. I think this looks, how is the vision now comparatively? It's still blur, or for me on my monitor, I would see
Blur, sir.
But we cannot help you beyond this scope, because I have moved 1 meter forward to the desk. Board is shrinked now, but this is our limitations I may find. Maybe networks also may matter. But I shall try best what I can zoom. Now I am making it to zoom. Now I am going back to withdraw. Now let's see whether this now at least visible to you. Let's see. Still you find a difficulty? Just try. View once more. Anybody else also can try? I think comparatively this is close. Please tell me.
Sir, remove all the, you have done the zooming, na sir? Do it the normal, sir. In normal mode, it will be more clear.
Okay, I'm just turning back. Okay, now it's gone completely other side. Okay, I'm just taking out the zoom. Okay. Okay, it's completely diverse. No, I'm making it 0. Means 1:1, like. I'm bringing it back. Okay, because there's a webcam attached side by side, and they are fine. Now you try to view it now. How you find this time? Any change you find?
From top to bottom, it is visible, sir. From left to right, it is a little bit cutted, sir.
Means it is now cutting. Width is getting cut. Am I right?
Yes, yes, sir.
I'll move it. Left and right, I can move. Nothing wrong in that. Now, can you see this visibility? I think
no, sir. If you go right side, it is left side is not visible, sir.
Now almost my
The
writing is no in on my screen right now. My writing, whatever I have done, whole thing is there. Nothing is cut in my monitor. That more
Yeah, sir,
symbol.
visible, sir. Yes, sir,
I
visible, sir.
no,
But
I'll do it. Some more I'll try. Some more. I'll try. Not an
no,
issue.
it's correct, sir.
Yeah, final test. Now I think left and right in my monitor viewing correctly. Even top and down also viewing correctly. You verify yourself once more and you'll continue. Okay.
Yeah, sir, it's correct, sir.
Okay, fine, fine. Maybe this is added devices are more, our systems are old, maybe technology change, maybe issue here. Let us work it out. Okay. Okay, I'll come back. So I was over here. Suppose if I have like a Y12, a mutual admittance between 1 and 2, another line between another mutual admittance between 1 and 4 if considered, how these representation will matter my y primitive was my scope. Therefore, y14 and y41 are one to each other. Let's say 0.1 more. Then I should represent this mutual coupling in this way. 1, go in the row number 1 and stop at the column number 4. Y14 I could represent 0.1 more. Similarly, 41, go down to the 4th row and column number 1. So this value will also get affected by this representation. This will become 0.1. Now I just conveyed you, if there exists a one pair means two lines having mutual coupling, you will have at least two elements in the system modified. It means to say this element 1 is having a coupling with 4, y14, y41 will have non-zeros in the representation. Like y12, y21 which represented you 1, 2, 2, 1, 2 non-zero. Like this, those many transmission elements in the system possess their mutual admittances. That many elements will be non-zero in the representation. This is the characteristic of a particular y primitive of the representation. So therefore, how do you use this? If this matrix is found in the original representation, I shall take this out now. When I had a matrix in this way, this is just to make you properties of y primitive understood. Basically, the elemental data will be on the main diagonal and mutual admittances will be on the off diagonal position. This is the characteristic. So we have an equation I bar plus j bar equal to v bar and a matrix y primitive. I was speaking over here. Okay. This primitive matrix is a matrix like this in this position. These v1, v2, v3 are the vectors of voltages. j1, j2, j3 are the vector of current. I1, I2, I3 are the vector of current. How many will be there? Suppose you have n bus or let me say n elements. It's like very clearly. N element system if I consider. There are n elements. Current in 1 like I1 plus J1 equal to V1 into this matrix. Suppose this matrix, it will be Y1. If there is no mutual coupling, only element 1 will be present, these will be 0. When I take a product of this with the voltage vector beside this vector, this also 1, this also 1 cross 1 here. That is product 1. Suppose it had a mutual coupling like this. This term won't be 1, V1, Y1 plus this term and this term like this coupling if exists in the system do matter your additional term over. It is nothing but one of the equation obtained from this. This is called matrix representation. Number of equations were compact in the representation. When I expand them, I will have several equations like a n element system if I consider. Surely I will have n identity like I1, I2, I3, Ik, In, J1, J2, J3, Jk, Jn, V1, V2, V3, Vk, Vn, and this can have n cross n dimension. N cross n dimension. Then I can expand equation 1, equation 2, equation 3, n equations I can write. So I am trying to give you a notice where all these are useful. These are useful in split of this equation. Individually, when you write the equation, these elements reappear in the RHS side. Voltage of the branch 1, elemental data 1. Voltage of the next, subsequent, relevant to your row, get represented over here to get your KCL value. This is a KCL. Current, product must be current. So this is how a KCL at each or KCL applied to each branch validated here. Like you have n numbers. In that perspective, when I multiply vector of voltage with these elemental representation, this is a matrix gets represented. So this is what the characteristics of an elemental representation in the primitive form can be understood. Now, what is the next application of this? Once we know primitive element matrix will have diagonal main elemental admittances on the off diagonal, which is a mirror here. Same as here. Here it is same like others. So they are the mutual admittances like this. Okay. I will take this to further interactions, which is how this is useful. This is useful to obtain Y bus by singular transformation. Singular transformation I would like to take up. So to obtain Y bus by singular transformation method, I have again a prerequisite called as graph theory. We need to know network topology. One need to know network topology. What do you mean by this? What is that elemental understanding we require over here? We need to take care. Okay. Ultimately, I require incidence matrices. Matrix A cap I write here, which is required to me. This is called as element node incidence matrix or element bus incidence matrix of a network in a graphical manner I need to obtain. So my beginning is over here. I would like to take Y bus of a system by singular transformation method. For that to happen, I need to have incidence matrix of a system. To obtain incidence matrix of a system, my primitive prerequisite is network topology. Without having much time invested in which, let us come to a graphical representation and let us take into. Let me put a graphical view of a network, and if you really want, I can project through my PowerPoint, which will be more clear to you how a graphical representation of a network of a power system can be done, how incidences of those elements with the nodes can be taken in the form of matrix can be analyzed. Okay. With this, I begin with the network elements and network incidence matrices. Let us take this. Okay. I just take it out. I just draw a matrix here. Let us take a problem here. I have a network problem. Let me write here. Okay. I write them as bus number 0 as a reference. I would say 0. This I write it as bus number 1. This as bus number 2. This as bus number 3. And I represent these elements as 1. I represent it as one more line I have drawn here. I just conclude here. So 3 lines from this 1, and I have represented this element as 2. I have represented this as 3, 4, 5. This is electrical network. There are 4 buses, 0, 1, 2, 3. I would have called this as a 1, 2, 3, 4 also. No matter. But for me to have clear understanding which of the representations is considered as a reference, usually 0 is labeled. This is considered as a reference. Until it is said 0 stand as a reference, If there is no 0, 1, 2, 3, 4 like that, bus labels were mentioned, the author should mention which is the reference bus taken for the consideration. For me here, no question, 0 I begin. So 0, 1, 2, 3, wherever is that 0 stand as my reference bus. So this is reference. Between reference and bus 1, I have a transmission element. Between reference and bus 2, I have a transmission line. Between reference and bus 3, I have a transmission line. Between bus 1 and 2, I have a transmission line. Between bus 2 and 3, I have a transmission. This is one rough sketch. This need not be a realistic problem. This can be a problem to understand connectivity and understanding of incidence of elements with a buffer. So my representation shall go with understanding the basic terminology. What is a graph? You need to know what is a graph. Then what is a tree? Like this way. Then what is incidence matrix? Incidence matrix and rule for that. I need to understand. If you are familiar with network analysis or electric circuit theory, you might have come across this network topology chapter. A graph or definition. It is the graphical representation of the electrical network with a line segment connected to buses and among them. It means graph of a electrical network is the graphical representation of the connectivity between the terminals or between the buses of the system. How many buses I have here? 1, 2, 3, 4. Physically 4 buses labeled as 0, 1, 2, 3. I have connectivity between individual buses. This is a physical layout of the transmission network. If I want to solve it by graphical mode, how do we solve? Using KCL and KVL. Analytically, we solve by KCL, KVL and other theorems which we have for reduction of problem. In a graphical approach, graphically we have to represent the problem. Graphically, we should apply the rule and reduce the complexity of the representation and solve at the final stage using KCL and KVL. Therefore, I would otherwise say graphical approach is also one of the interesting approach to solve electrical problems. May like KCL, KVL, how we used to solve for the unknown, the current through a element or a voltage across a element. We would like to know. We have a conventional approach, branch approach, loop approach, some direct approach theorems we do have, like Norton theorem, Thevenin's theorem, superposition theorem, reciprocatory theorem, and we have Telegen's theorem, Millman's theorem. So many star delta network reduction we do have. This is another approach through graph theory that we call it a graph approach, graphical approach of solution of numerical problems of a network problem or power system problem. For that, I need to know some definition. Then when I have a representation over here, the first definition what I should know is graph. What is a graph? Graph is a graphical representation of interconnection of elements in the system between the buses. It should contain all the elements. It should contain all the nodes or buses. It should represent or depict the connection between each one of them by line segments. That representation we call it graph. If I want to represent this electrical parameter, there are voltage source, there are current source, which are eliminated. It is the elemental representation only. Then a graph of this network can be drawn like this way. If I want to represent a graphical way, how many nodes are there or buses are there? 4. I put a dot here. Like this, I put a dot. I call them as 0, 1, 2, 3. Then I'll just connect them. I connect one by one. There is an element, connect it, connect it. Then I connect this. You can see this. This became reference. This became 1, 2, 3. Then I label them This is element number 1, element number 2, 3, 5, 4. This is called graph. Graph is a graphical representation of the electrical connection of a system incorporating all the buses and all the elements and depicting the connections of that graphically, connecting them by line segments. Maybe this was having some impedance, this was having some impedance, this was having a mutual coupling, whatever. So it's just taken off. Immediate connection between the element to bus is represented by line segment. It shows there is a connection between bus 1 and 2 by element number 1. That's all. What is the value of element number 1? Initially, we will not worry. When we confine a matrix, when we reduce the information, finally at the conclusive state, elemental data is used to solve numerically. Till then, it is a graphical approach to reduce the complexity of the problem. Therefore, my immediate task is to represent it into a graph. A graph is having several nodes and several elements. Elements got connected to one another to the respective buses or nodes. However, the connection exists in the original diagram. There is no voltage source, there is no current source represented in the graph. This is also known as planar graph. There is no crossing of lines, planar on the same plane. And now there is no orientation. I would otherwise say this is a graph. Graph should have some arrow of connectivity, flow of current, something like that. We'll see that very later. This is just a connectivity. Then graph, I may have orientation. What do you mean by orientation? Suppose there occur flow of current in this element. Suppose if I mark this, let us say arbitrarily I will mark. Later I will delete it off. So let us mark them. I don't know what is this marking I am doing. Simply I am doing marking. Can you see some change in this now? Yes. I have put an arrow here, arrow here, arrow here, like this way. This is called oriented graph. This is not only graph, this is now oriented graph. What is the meaning of this? This is a graphical representation of the electrical connectivity of the power system, having identified the directions of flow on each line by arbitrary manner. So I have put an arbitrary direction 0 to bus number 1. There is a flow of current. Naturally, current flow from higher potential to lower potential. It is known to us. It is a practice to give some arbitrary convention if nothing is put. If it is already put, we have to follow the direction. So, therefore, I have marked up going arrow, left moving, right moving, down, some arrows. These arrows are nothing but orientation attributed to each element. I have 5 elements. Each element got oriented by a direction and got connected to respective buses. This we call as oriented graph. Oriented graph do contain all the edges. I use the word edge. Edges or elements and all the buses. Nothing is clipped off. We have all 4 buses, all the 5 elements as usual in the problem. This is just transforming it physical electrical network into graphical representation where there is no elemental data, only numbers are represented. This is called oriented graph. Now, the next definition which we need to understand is tree. What is that tree? If you go back to the basic definition, tree is a graph. Tree is a graph or it is a subgraph of a main graph. See the representation. Tree is a graph or subgraph of a main graph in which no closed path exists. What is the meaning of this? Tree is a graphical representation of a problem. It is a graph. Tree is a graph which is having orientation and there exists no closed path. Then there comes the question, how come I would define no closed path? Then I will come back to this point. Is there any closed path? Yes, absolutely. Can you trace this? This is a closed room or closed path for the current if current flows. There exists another closed path over here. There exists an outer closed path for current to flow. If I am not wrong. This is called closed path number 1, closed path number 2, closed path number 3 from outer edges. So such closed paths do exist in graph, but not in tree. Tree is a graph or a subgraph in which no closed path exists for the current to flow. Then question comes, how do you form a tree? Tree is obtained from a given graph by making some of the elements dotted, leaving remaining elements solid. Then comes elements called as twigs and links. Twigs and links. Some books refer branches and links. What is this? Let us make this again. I redraw it better. So I redraw it once again. I connect back. Okay. I connect it back with all the terminologies which I referred. 1, 2, 3, as usual, 0. This was oriented 1, oriented 2, I mentioned. I hope I mentioned downward. 3, I hope I mentioned this also downward. No matter whether it's the downward or upward, for me it is just to represent to you how a tree is formed. That's it was the original example of oriented graph. What is a tree? Tree is a graph or a subgraph in which no closed path exists. Suppose you just imagine this line I delete by a dotted line. Can you expect a closed path over here? If this is broken, there is no closed path. I eliminated element number 1 between 1 and 2 by dotted line. Solid line, dotted line. I call this dotted line as links. Solid lines, I call them as twigs or branches. So when I have a solid line got represented as a dotted line, there is a break of path. Hence, this is no more a closed path. I did personally one element dotted. Then one of the closed paths got broken. Still, how many closed paths are there? There are closed paths over here. This is one closed path remaining. How to break this? One more element I have to break. Suppose if I break this line, let's say nothing wrong in that. Whichever the line you want, you can break to see to that whether that establishment come or not. Now, can you see there is no closed path if I remove this line? Then similarly, outer closed path which I found, that also got broken because you cannot form a closed path with this. There is a break, there is a break. You cannot make a closed path here, there is a break. You cannot make a closed path here because there is a break. You cannot make anyway, you cannot make a closed path. So therefore, tree is a subgraph or a graph in which no closed loop exists, which is comprising of several twigs and links. Links are the ones which are put with a dotted representation to form a tree only. If I make them solid, it's going to become again original oriented graph. Therefore, the elements of the representation which are put with a dotted line called as links. The elements of the representation which are solid by representation which are called as twigs or branches. Oftenly, number of solid lines were represented as dotted lines to form a tree. Now, I would like to ask, is this a tree of a particular problem? It must be, because of the representation which is called oriented graph, few of the elements we deleted. We deleted few of the elements and we could get this number. You may ask me how many elements we should repeat. So if you go back, there was a link L equal to L equal to n minus b plus 1. Not n. B L equal to E minus n plus 1, where E is the number of elements, n is the number of nodes, plus 1, nothing but number of links. If I put it in this, there are 5 elements minus number of nodes, 1, 2, 3, 4, minus 4 plus 1. This represented you 2. It means in this particular oriented graph, you have a liberty of eliminating any 2 lines. This L says how many links you have to show such that such an representation become a tree, which is number of links in the system equal to number of total elements minus number of nodes or buses plus 1. If I use this formula, I'll get a number. That many elements, whichever the element, by count that number, if I put dotted, I must see to it that all the closed lines possible got eliminated. Then my tree formation is perfect. Now, if you find 1, 2, suppose somebody may be wishing rather than 1 and 3, if I make 1 and 5, eliminate it. You look into, suppose if I draw another representation, how is that? 4 I'll make dotted. Let us see. So 4, 0, 1, 2,
Sir, it is looking all
3.
blur.
No, it's very clear on my screen here because it's a fine-tuned value only. But only thing is we have to bring the camera completely to the close. We shall try. Okay. So you put a message to HOD, please. It will be very nice because we are wasting our time in adjusting only. Because I am single in the hall, making all these things. On my screen, I am able to get, but how could you are not getting? I am really worried. Now, can you put a message to head of the department in the group? Clarity is not there. If it is the difficulty, please put into group so she can view with some support. Okay. If I start attending, no, my class will run. That's the problem. Okay. So, but for me here, it looks clear because I have not touched the camera. Once after having touched it, I have not touched it. Okay. I shall see and I'll inform her also. Please put a message to madam also. Okay. It will be nice. Maybe your network connect and disconnect once. Let us try. Okay. So I will represent 4 dotted, 1 solid. Let's see. 1 solid and 5 dotted. Okay. This is downward. This is 5. And these things I put solid as usual. This was 3. This was 2. Now you see 2 lines I put dotted. Still I will not get closed lines. This is a broken. This is a broken when this is also broken because there is no closed path possible. So pattern 1, pattern 2. Now I would like to give you a mathematical link. There are a number of trees are possible for a network problem. This is a problem. For this, one of the tree pattern, second tree pattern, third tree pattern, like that. How many you will get then? Called A into A transpose. A matrix into A transpose of matrix. If I take operation, it gives you a scalar number. A matrix into A transpose of that, if I take, it will give a number. That many orientations are possible. That's called as number of trees of a problem is scalar of A dot A transpose. No question comes, what is A? That's what my beginning. I took you to the application, made you confirm what exactly I require. A matrix is my need. A matrix comes whenever I find a graphical representation. Whenever I find graphical representation of a network. So I made you to just to know a topological representation of a problem by a graph which is oriented graph. Then tree is formed from the given graph by by eliminating few of the solid lines by dotted line. The number of dotted lines to be present in the oriented graph, to speak it as tree, is defined by L. L equal to E minus N plus 1. If I operate that many number of elements, if I put dotted on the representation, that representation automatically from the oriented graph becomes tree of that problem. That is very necessary for us to our further interaction. So next, after having basics of which is got, I go with the incidence matrix. What do you mean by incidence matrix? Because you've got to know somewhere, when a tree is formed, after the obtaining of tree, mathematical operations must be performed. How do you perform mathematical operation? You have to compact the representation of elements and nodes by their relationships. That relationship of element and node must be put in the form of 1 and minus 1 or 0 in the matrix form by using a rule. That relationship, incident or not, connected or not, connected towards or away from that, that understanding relationship is mathematically represented as incidence matrix. So that we need to begin with. That's called incidence matrix. Actually, I wanted to begin over here. This is a prerequisite knowledge one should have, how graph theory is important, how a graphical representation, oriented graph, how oriented graph become a tree, how many trees are possible for a given graph, one should know. So once we have this, I come to my basic need, incidence matrix. Okay, because that is my beginning of wide bus by singular transformation method. No matter I am going slow, but it should be clear to you. Incidence matrix I am trying to write. For this, I take a simple problem, very simple problem. Let us put an incidence matrix like this. Let us take an example. I just take an example and I'll give you a rule how I do it. Okay, I connect it. I connect this way, and I have a representation this way. I label them. 0 I have here, 1 I have here, 2 and 3. Hope you are able to understand my representation. It is a graph of a electrical network. I have some random orientation given, and I have numbers put on each element. You just check it out. I have given orientation. This is a graph of a electrical problem where sources are eliminated. Interconnection is represented by elemental reconnection. Then I label them 1, 2, 3. I have 4. I have 5 and 6. There are 6 elements, 4 buses in the system. Now, my task is to write incidence matrix. It is also known as element node incidence matrix. Element node incidence matrix.
Sir, repeat sir, from start.
Yes, I repeat it. It is known as, basically I am trying to understand incidence matrix. There are incidence matrices are there. Number of matrices are there. Among them, the first one I am trying to utilize, which is called as element node incidence matrix, which is known as A cap or A bar, we call it. Book to book, there is a small change in representation. Some book refer A cap, some book refer A bar. It is nothing but element node incidence matrix or element bus incidence matrix. It should be a representation of all the buses, all the elements, how they got interconnected to one another. That relationship I am going to confine into a matrix by a rule, simple rule. So I have an example. I have 4 bus system. There are 6 elements in the system, and all the 6 elements got oriented by direction. You may ask me, how would you give this direction? Arbitrary. If it is given, I will use. If not given, I will make my own arbitrary direction. I will follow it. It means once you have given or you have given yourself, you have to use them till the completion of your presentation. If it is already given, you should use them to complete your observation, like that. So you may ask me 1, 2, 3, 4. I have given arbitrarily, and I will follow and I will complete the derivation. So therefore, I have a system which is a graph of a system with the orientation mentioned. My task is to write element node incidence matrix. It means all the elements of a system, how they are connected to the system, which element is interconnected, incident to the element 1 with the bus 1, element 2 with the bus 2, element 5 with bus 1 or not, 3 or not, 2 or not. I will observe, I will enter the relationship in the matrix form. How to do it? So I have a rule. The rule says Aij. Let us say Aij equal to +1 equal to -1 equal to 0. Where it is used? The element of matrix A cap let me write here A cap equal to, I put a matrix form here. What is the dimension of matrix? Question comes to our mind. Yes, A cap or A bar is known as element node incidence matrix. How many elements are there? I should know. How many are there? 1, 2, 3, 4, 5, 6. So element by number, I have 6. How many nodes are there? 0, 1, 2, 3. Physically, I have 4. It means this matrix A cap will have a dimension 6 cross 4 or 4 cross 6, depending upon the book you are referring. If you refer Tag and L Abiyad textbook, elements are put in this way. Elements and nodes in this way. Elements are put down, number of nodes are put across. It means to say, if I represent it in this way, I will be having 1, 2, 3, 4, 5, 6. So these are elements. How many nodes are there? 0, 1, 2, 3. So I'll put a bracket here. Okay. So this will be E cross N. E stands element, N stands number of buses. It is E cross N. Now, what is the element at this position, this position I should do? To do that, look at that. The rule says you have to go column. What is the column? O here or 0 here? Look at the bus number 0. Come to this position. Look at the column number 1. You have to fill all these things. Complete it. Go to column number 2. Go down. Go to column number, means bus number 2. Complete. Bus number 3, you complete. Likewise, each bus, one at a time, you have to observe, you have to apply the rule, and you have to incorporate the representation. How to do it? Let's say, suppose if I want to fill entries of this, what is the meaning of this? At bus O, I stand and observe whether element number 1 is incident to this. It has a connection with which or not. I should establish. At this O, 1 is going out. Yes, there is a physical connection. Then 2 is no way connected here. 2 is no way having incident, not incident. No incidence of that, not at all connected. Hence, it is not connected to this 0. Then bus element number 3 with bus 0. How is this 3? 3 is far away, no connection. It is through this, not required. Physically from this, is it emerging out or coming towards that? I should check. 1 is having connection, it is emerging out. How about 2? No way. 3, no way. 4 is here, no way. 5 is going out, it has a connection. It is incident to O. How about 6? Incident to O. No doubt is coming towards, but incident. How many elements in this column are connected to bus number 0, I have to think of. For that, think 1 has a meaning, 5, 6. 1, 5, 6 are physically incident. Remaining 2, 3, 4 are not incident. Then the rule says elements of the matrix A follow a rule Aij. Aij means it is the ith branch incident to jth node or a bus. Suppose ith branch incident to jth node and oriented away from that +1. Oriented towards that -1. Not at all incident 0. I repeat that. The elements of this matrix, how it should be filled. To fill the elements of this matrix, I should say a rule Aij refers to element of a matrix A, an ith branch number I, incident to jth bus or node, incident and oriented away from that ith branch, incident to jth node or a bus, oriented away from that is +1 entry in that matrix. Now look at this. Branch number I is say 1. I am here 1. Element number 1. 1, let me write here. A1O. A1O. Element, ith element, incident to jth node, ith element, incident to jth node, and oriented away from j, away from that, nothing but +1. So in this position, I'll get +1. Then,
Excuse me, sir.
yes, please.
Sir, we are having testing and commissioning class now.
Okay, I'll break immediately. Another 1 minute. Okay.
Yes, sir.
Another 1 minute. I'll break. 3 lines. I'll complete. I'll break it. Okay.
Okay,
These 3 lines,
fine, sir. No problem.
okay, because this will be beginning for me in the next class. Okay. Aij, when I have ith element incident to jth node and oriented away from that is +1. Like example, element number 1, it is connected to bus number O, oriented away, and its representation will be +1 over here. How about bus number 2, element number 2? Element number 2, like this way. A20. No way it is connected. Directly it is third rule, not incident. And element number 3 is here, not incident. Element number 4 is here, not incident. Element number 5, you can look into this. It is A50. Element number 5, incident to 0th bus, oriented away from that, it should be +1. And 6th element, A60. It is 6th element, incident to O and oriented towards that. Oriented towards that means second rule. And ith branch, incident to jth node or bus, oriented towards the j is -1. Away from j is +1, towards the j is -1, not at all incident is. This is the rule. Ith element is not incident to j, 0. Ith element is incident to j, oriented away means plus, oriented towards means minus. Now I can say 6 is towards this O, this becomes minus. This is the entry. So look into this. Outgoing, incoming. I can say whenever there is 0, not at all connected. Like